Haiku arm, my favorite BeGeistert topic.
Left or the right arm?
um, Either one will do. The one that works. Status plans, dreams. Well, I guess we won't get very much further than plans, but and status. But
Wir
pretty
hatten
much.
welche.
Hatte welche, jetzt geht's wieder.
Also,
Oder
also ich glaube, der Anschluss ist sehr wackelig. War angeschlossen und kam ein Strom. Jetzt haben wir. Dafür, aber da kann man die Größe gar nicht einstellen. Wir müssen die Schärfe einstellen.
Do you want to start again? Yeah. Okay, I'll start again.
Only for your makes your editing easier.
Go. Well, Haiku arm, my favorite BeGeistert topic. Yeah, I had to restart. So, whichever one works will do. No, I haven't got much time to work on Haiku normally. Between BeGeisterts, but every BeGeistert I spent my coding sprint on ARM, on the ARM board, which has been going on for, well, even before I got involved. There was already work being done on it for a year or so, so I guess it's 3-4 years now since the first changes were made. Well, the goals set are fairly basic. We just want to implement some support for the ARM architecture and support the popular ARM boards, mostly focused on not as much on tablets, but on the separate small PC board styles, because they're the best fit to the way Haiku works currently. It's not really built for touch and such yet. There's somebody working on that, but for now that's the main focus. That's also where we can probably get the most reuse of the existing drivers like USB and such, and get keyboard support and such. Quickest way to a usable device. Now there we're already touching the problem on ARM. There are many layers of hardware support required, from the SoC, which is more or less similar to the CPUs, existing of the ARM core, which is the core CPU, to boards and peripherals on the boards, but it's all very custom. I'll go through the different components right now. That small little piece there is the part that we've done most work on so far. That's actually support for the ARM core, and unfortunately the actual ARM core CPU IP comes in many different shapes and forms already. The oldest one we support is ARM v5. That's what I started with because it was very well supported by QEMU. So I took the Vertex target. Unfortunately, there's some problems on the older architectures, 5, 6 even partially, with atomic operations. There are basically no support for proper atomic operations in the CPU. So we're using, for the ARM v5 support, we were using a trick where we were using system calls for the atomic operations, and basically disabling interrupts and holding spin locks while doing the atomic operation. Now that ARM v6 has some atomic operation support, mostly for 32-bit values, not for 64 bits. So there we go again. You get the same workaround. And on ARM v7, they finally have proper atomic operation support for both 32-bit and 64-bit. So there we can use our inline atomic operations again, which makes the whole system, well, besides being more performant, it makes the code more easy. So in between last BeGeistert and this BeGeistert, someone decided that it was just much easier to switch to ARM v7 and forget about the old legacy support, which unfortunately broke a few things again. And although about the time I started with my work on the ARM board, ARM v8 came out, which is a 64-bit based architecture. There's absolutely no support in the ARM board yet for that, except for the stubs taken from the 64-bit support from x86 in the VM. At the moment, we're really only focusing on v7 boards, like the main target currently being the Beagle board, but the other ARM v7 devices should be fairly easy to add in the future. Now, if we look there, the ARM core isn't actually a separate chip. It's really just a bit of IP from ARM that's being used by SoC manufacturers. System on chip, it stands for, which is the core CPU functionality plus a lot of additional peripherals included. I2C, SPI buses, SD controllers for storage, NAND controllers for storage, etc. Now, those additional IPs are either bought in by a SoC vendor, in which case you might be lucky and actually be able to write a driver that's usable on multiple system on chips. But very often, especially for the more basic stuff like UARTs, like I2C, like SPI, the more simpler IP, the vendor ends up writing it themselves, so it's cheaper for them not to have to license. Which means there's a hell of a lot of these things to implement if you want to support a wide range of system on chips. Very, very little standard there. Same is, of course, unfortunately also the case for interrupt controllers, timers, clocks, which are fairly critical to have working early on your kernel boot up. At the moment, that's actually still hard-coded to our old Vertex target in the kernel code, so that will have to be fixed as well. I hope to get that done this week during the coding sprint. Now, bit by bit, there's more standardization happening there. ARM has standard IP that they're licensing out to their clients for interrupt controllers and timers. So the more recent ARM-based system on chips all more or less use the same IP or with very little customization of the original ARM IP. So there's definitely some consolidation going on, which will make our life easier, but there's still a lot of custom code to write. Now, besides that, in the end, even if you have the SoC handled, you've of course got the board, the actual board with additional peripherals on there for phones. That's of course the sensors, the 3G module, but on those boards there's usually quite a few, well, your buttons, of course, any buttons that are on the board, LEDs on the board, etc. So there's more drivers to write there, although these chips are usually fairly standardized, and there are quite common ones there as well. But there's no discoverable bus on a PC. There's either for the onboard stuff on the motherboard, ACPI can do a lot for you, and on higher layers you've got your PCI bus and such that you can actually enumerate and check, hey, what do we have here? On ARM there's basically nothing like that. So in previous times they found a solution for that I'll cover later, but in older times it meant that, for example, in the Linux kernel, for every ARM board you had a C file that declared which devices were on this particular board. So you had a lot of these files laying around with code to tweak and attach the right device objects to the right bus, hard coding interrupt lines, IO addresses, etc. which was an absolute nightmare. Now, to fix the problem with a non-discoverable bus and be able to reuse, to make more reuse in the code available, they took something from history. They took something from what's known as open firmware or open boot. Was used a lot on, and still used a lot on PowerPC-based platforms. For example, IBM Sun used it on their devices. Where open firmware is a complete environment, a kind of BIOS style environment. One particular part was taken out of that, called the device tree. These alternative BIOSes provided the operating system or whatever booted on top of the hardware with an actual device list. So a binary tree basically containing all the different devices available on this particular machine. That was fully the format of the tree was fully standardized. Here's a little part. Here's a little part of it. I just grabbed a random bit, but it shows there's a textual description that gets compiled to a binary blob. But it even lists the different CPUs, the clock frequencies, the cache details, and so on, including standard descriptions for I2C buses, etc. Now you see I actually missed a useful type, but useful bit. But there's even possible to specify the type of a device from several levels, from a very generic name for an I2C bus to the vendor-specific one. So the drivers can check basically a string, a signature, to see like, okay, do we have a device that matches this type? And that's all string, so it's fairly flexible in comparison to the three magic numbers on PCI specifying the type of device. Oh, yeah. So my intent for this week is actually get a very minimal version of device tree support working in the ARM port. So at least the kernel can see, can detect on which socket's running and choose the right interrupt and timer implementations to use for the hardware it's running on. I might even build some FDT support into the bootloader, which is currently hard coding, or at least hard coding at compile time, where it gets loaded and where it finds the different hardware components that it needs to access. But my main focus is on doing that for the kernel, because in the end we should actually have a proper device tree bus manager, like the PCI bus manager, that drivers can register to, because we need a boot device. But I'll get back to that. The current, and back to Haiku after the introduction of the ARM platform. Current status is the bootloader actually starts and loads the kernel and starts the kernel. The kernel actually starts but crashes in one, runs into a VM mapping problem that I'm still trying to sort out at this point. Once we get past that, we've got another problem. We actually don't have a BFS volume to boot from because we don't have a boot device supported yet. Now my plan is to use USB for that, to make a minimal device tree bus manager, basically reusing what I did on for the kernel by then, and enable the USB stack to run, which should give us the ability to boot from a USB stick or an external USB hard drive. I actually had that working through a hard-coded hack on Verdex already. It saw a memory, a USB stick on the USB bus. And of course, there's there's still, well, very little to no userland support in the kernel. The VM code has really only been tested through the kernel flow. There's no, at least no tested code. There's a little code there that assumes it can start a userland program, but I'm far from certain that that's correct. So there's work to do there. Hopefully I'll get most of this done. Hopefully I'll get to a crashing userland app, probably Bash, by the end of this week, and then it should be just some more debugging. As I said, my next steps, my plans are fixing the blocking memory management issues that I'm seeing currently. Implement minimal device tree support. Add the drivers for the OMAP chip that we're targeting currently, for at least for the interrupt timers and the real-time clock potentially. And then build it out to a proper bus manager so we can enable drivers, and especially the USB drivers initially, to support the device tree. And then boot Haiku ARM from a memory stick. Yeah. No. Can't do without a demo, of course. So I actually prepared something. Let's hope it works. That one. Then okay, the window was too small. But as you can see, the bootloader actually completely completes. Even the frame buffer shows. You can there see the last bits of the Haiku logo. The icons being displayed, but unfortunately, as I said, the ARM VM translation map, the kernel crashes due to, well, it actually finds an address already mapped that it's not expecting. That's mapped by the bootloader and is still intact after the VM initialization, which it shouldn't be. So I'm trying to figure out what's going wrong there. But even KDL works. I can't type here now because on serial I can, but on here I. But KDL is fully functional. Backtracing works, and that's the current status. Yeah. Any questions?
What do you do tomorrow?
Well, I hope tomorrow these icons will light up before the KDL screen comes up.
Pretty pictures.
Pardon?
Pretty pictures.
Pretty
cool.
pictures, exactly. Yeah, I mean, it's the typical cycle of getting one step further and seeing the same KDL screen pop up yet again.
Can you already build packages for ARM?
Yeah, the whole bootstrap process works for ARM, so that's not a problem. The real problem is actually getting the basic system up and running. Then the rest should come along easily.
The bootloader currently loads the kernel and the modules from a
floppy disk. It's basically we're using U-boot, and we create a U-boot image containing the boot floppy image in the stage 2 loader. So the stage 2 loader finds the TARFS file system, loads the kernel, the modules in the kernel from there, and starts the kernel, because we have no boot volume yet. So, and there's not something easy like the BIOS to scan for your boot volumes and read a bit. So this is the only way we'll ever be able to boot, really. Yeah. Any more questions?
Okay, great.
Yep.
So the V6, so getting it to run on a Raspberry Pi would then need something that patches for these missing atomic.
Yeah, actually the biggest problem there is not so much even the atomic operations, but is we're currently compiling with hardware floating point because most of the V6 actually have hardware floating point as well. But the ARM V7 has a newer version of the hardware floating point, and the problem there is getting the tooling, the compiler set up correctly. The thing is that our bootstrap process assumes that whatever the compiler sets as default is whatever you want to run. Basically, the default is the correct target. You can't really, or you couldn't, at least early on, pass any specific compiler options to Haiku Porter to say optimize for this CPU or use this version of floating point. So at the time you build your cross compiler, you have to select which target, basically which ARM version you're building for, and that's the main issue currently. We should actually, since we're now at configure time choosing the board you're building for, check what the proper defaults are for that particular board and set up the GCC compiler to default to that. It's mainly the main problem here is that our build system is not working with multi-lib support. That's the core issue here, really. If we could fix that, and I've had a look at that, but that's fairly non-trivial to fix, and we could get some way to pass compiler options to Haiku Porter. For building the bootstrap images and the packages, then we would actually be able to easily build for other versions than ARM v7 as well. But there's quite a bit of build infrastructure to massage there. That's basically why it was decided to switch over to ARM v7 for now. So we have a target that's fairly easy to support, and skip the old ARM v5 because it was just too much hassle. I mean, ARM v5, these devices are really not here even anymore. Anything that's been produced in the last year or two is pretty much all ARM v7.
Except for the Pis.
Except for the Pis.
Yeah.
I agree.
Yeah.
And as I said, I suspect that once you work around the build system issues that we have, the Pi will compile and boot as far as the Beagle board does now. Yeah. Maybe some patches are needed in the code because the build hasn't been run for a while. I'm hoping to check out if I can hack one up today.
Well, I've got one. Olivier's got one.
Yeah, exactly. So we can see if that's still.
And I've got keyboard and mouse, and we have a screen.
Yeah.
I don't know actually.
Well, not for the. Oh yeah, for the Pi it works.
We have a screen.
Yeah. So yeah, that's another more long-term thing we'll have to look into, the build system issues, or at least decide what we want to do. We could split up the. Currently, we're saying ARM covers all the ARM architectures, like the ARM platform, the ARM support in. The ARM target in Haiku supports that. We could even decide to say we do an ARM v5, an ARM v6, and an ARM v7 or so. So they're separate targets. So then you set up the tool chain for one specific architecture.
It's like 6, 7, and 8. I would have thought.
Yeah, I mean 5 doesn't really have much make much sense anymore at this point. We've got a decent emulator for the Beagle board and such as well these days. So yeah.
Thank you very much.